I promised an applied example of finding the area between two curves and why one would want to do that. So this is an example from economics and social theory, and it has to do with the distribution of wealth in a community. This community could be a country or a state, a county within a state, perhaps a city. But if we had perfectly even distribution of wealth, then 10% of the people would control 10% of the wealth, and 20% of the people would control 20%. And we could say in general that X% of the people would control X% of the wealth. Now that would look like, on a graph, something like this. So here are my axes. And let's put wealth, I'll just put a W here for wealth, on the vertical axis, and let's put people on the horizontal axis. And this would represent 100% of the people, no percent of the people, no percent of the wealth, 100% of the wealth. If this wealth were perfectly evenly distributed, then this line, straight line, not bad, which I'll label X, would be the graph of the case where X% of the people control X% of the wealth. For example, if we come over here to maybe 25% of the people, up and over, about 25% of the wealth. 50% of the people, 50% of the wealth. That would be a perfectly even distribution of wealth. It seldom happens that way. In fact, I'm sure it never happens that way. So here's some data from our textbook. And this is hypothetical. I don't think this represents any real place. But this is simulated data where I've got the percent of the people in this first column and the percent of the wealth in the second column. So this tells me things like 40% of the people control 31% of the wealth. 80% of the people control 78% of the wealth. Or another way to say the same thing, the top 20% of the people control 22% of the wealth. So this actually represents a country or a county where the wealth is fairly evenly distributed. I could put this distribution of wealth on this curve by just plotting points and then kind of schlepping a line through the points that I'd plotted, Cartesian coordinates. Or I could use something called quadratic regression. And quadratic regression will fit a degree 2 curve through these points. And not just any curve, it'll be the curve that minimizes the square deviation of itself from these points. So it'll be a good curve in that sense. And if we would use quadratic regression, which we can easily use using a spreadsheet or using our graphing calculators, if we would use quadratic regression to fit the best curve through these points, it would look like f of x is equal to 0.3125 x squared plus 0.7175x minus 0.015. That's a quadratic function that best fits this data. And I'll just sketch what this quadratic would look like. We know it's going to look like a parabola because it's quadratic. It's a squared term for the highest degree. The coefficient is positive, and so it would open up. And it would look very much like this little curve that I'm drawing right here. So the graph in yellow, which we'll label as f of x, is a graph that tells me what percent of the wealth is controlled by what percent of the people. And that's known as a Lorenz curve. A Lorenz curve. And of course the Lorenz curve is a measure of the distribution of wealth. But what we'd really like would be a number, an index, that would summarize for us what the Lorenz curve is trying to tell us. So I'm going to scroll up just a little bit here, get a little more room to work, and define for you the Gini Index. And the Gini Index is a single number that will tell us about the distribution of wealth within this hypothetical community that we're looking at. Now the Gini Index is a ratio of two areas. It's the ratio of the area under the blue line here between 0 and 1 and above the horizontal axis. So that's a triangle. So that's the area that we're going to compare to. And what we're going to compare to that area is the area between the Lorenz curve and the blue line. So we're going to be comparing the area between two curves. And of course, it's not just a coincidence that the area between curves is what we're talking about right now. So I'm going to try to calculate this area, the area that I've indicated with little green arrows, and the Gini Index will be the ratio of the area under the blue line. Now that's a triangle and it has an area that's really easy for me to compute. It's half a square of 1 on a side, and so the area of that triangle is 1/2. I'm going to compare this area in here to that 1/2, compare in the sense of I'm going to take a ratio. So I'm shading in the area. I need to find this area and compare that area by putting it in the numerator here over 1/2, and that ratio will be the Gini Index. Now, can I find that area? Do I know how to find it? Well, actually, yes, I do. It would be the definite integral from 0 to 1 of x minus f of x dx, where x and f of x have identity as depicted in this graph. Now, dividing by 1/2 is the same as multiplying by 2, so I can refine here my Gini Index a little bit. I can call it 2 integral from 0 to 1, and now I can put in what x and f of x are. So x is, of course, is x minus, and my f of x, here's my f of x, so I'm going to put a parentheses here, and this would be 0.3125 x squared plus 0.7175 x minus 0.15, decimal point goes right there, dx. And so that integral would be the Gini Index. It was divided by 1/2, now it's multiplied by 2, which is the same thing. And let's once again scroll up a little bit, and let's evaluate this integral. Now I could do this by dropping the parentheses and combining this x and this x right here would combine and then integrate, or probably just about as easy to just go ahead and integrate in the shape that it's in right now. So now I'm going to evaluate the integral. When I evaluate the integral, of course, that will use up, in a sense, the integral sign and the dx that tells me what to integrate with respect to. So when I evaluate the integral, I will have an x squared over 2, and then I'm going to, I don't want to lose sight of this parentheses that's preceded by a negative, so I'm just going to stick it out there and go ahead and integrate in here. 0.3125 x cubed over 3 plus 0.7175 x squared over 2 minus 0.015 x And that was a definite integral between 0 and 1, so I'll put the 0 and 1 out here, indicating that I still have to evaluate this whole expression at 1, and then subtract from that what I get when I evaluate this expression at 0. And let's take just a second to look at this. This is going to be especially easy because these x's that get raised to powers, they're going to be 1's raised to power, and 1 to a power is just 1. And then when I have to subtract what I get at the lower limit, well, every one of these has got an x in it, and x will be replaced by 0, so at the lower limit I'm just going to get 0. So that's going to make this particularly easy to calculate. So I'm going to write down right now what I'm going to get. So there's the 2 outside. Now put in a 1, and I'm going to get 1/2. So you see how this is going to go. 1/2. Keep the minus in the parentheses for right now. This is going to be a 1. So we'll have a 3125 over 3 plus a 0.7175 over 2 minus a 0.015. Now that's what I get at 1, and what I have to subtract off would be what I'd get at 0, but we've already reasoned through that and we know that's going to be 0. So what do I do now? Well, that's all just numbers, and so I'm just going to use a calculator and do the arithmetic using a calculator, and I get a Gini index of 0.104. Now what does that tell me about the wealth in this particular community? Well, let's think about that for a second. Let's draw another sketch. Now if I have, here's my axes again. This will be 100% of the people. This will be 100% of the wealth. And if my wealth is perfectly distributed, it would look like that. If the wealth is perfectly distributed, my Lorenz curve will also be that yellow line. And so if I would take the area, this would be when perfect equality of wealth. In the case of perfect equality of wealth, my Lorenz curve and this yellow line would be the same. So the area between the two would be 0. So my Gini index would be 0 over 1/2 would be 0. And if I had a perfect inequality, complete inequality, well, if I had complete inequality, I would have a graph that would look something like, maybe something like this. Here's my wealth. Here's my people. 100% of the people. 100% of the wealth. Okay, that's the vertical line that would be the graph of perfect equality in wealth. Now, if in fact I had perfect inequality, then 50% of the people would control none of the wealth, 25% would control none of the wealth, 75% would control none of the wealth. So my Lorenz curve would look like this until it got over to the last family, the last 1%, and they would control all the wealth. And so my Lorenz curve would suddenly take a jump up to one family controlling 100% of the wealth. Now what's the area between the orange and the Lorenz curve. Well, now the area is 1/2. So in this case, this is a case of complete inequality. The Gini index is going to be 1/2 over 1/2, which would be 1. So a Gini index close to 0 is, I think I'm writing off the page here, Gini index close to 0 is good distribution of wealth. In our example, we have a Gini index of 0.1. Of course, that's not perfect, but the Gini index of 0.104, not bad. In fact, certainly better than most places in the world. The wealth is more nearly distributed. I think this is made up data, but it was interesting to work with. So this is an application of area between curves, going way longer than I intended.